On slide 35, we turn to example 2 having to do with depression and disability. So this example is from the Ormel et al. Article of 2002 that I mentioned in the background section. So this was published in Journal of Gerontology and was not noticed by methodologists in the panel data area. So what we're looking at here is disability at 3 time points and depression at 3 time points. This is for 753 people, and the 3 time points, as we mentioned, is the minimum that you can get away with for doing both RI-CLPM and the new reciprocal RI-CLPM. So the Ormel et al. Model has a disability trait or a random intercept influencing all time points, correlated with a depression trait or random intercept. And in addition to that, we have cross-lagged effects across time, lag 1 effects, plus we have lag 0 effects, reciprocal lag 0 effects. So that is what we call the reciprocal model in this talk. What we're looking at here is an analysis where we have measurements at 1 year apart, and this figure comes from figure 2 in the article, presenting standardized estimates after fixing these 2 reciprocal effects from depression to disability at the 2 time points, fixing them at 0, having found them insignificant. Now on the next page then, we conclude that this reciprocal RI-CLPM has the same kind of finding that we saw in our MWI example. One of the reciprocal effects is found insignificant. Small negative effect in this case, which would not make sense even in this context, whereas the significant effect is positive and larger. So that's why the small negative was fixed at 0. So the analysis uses time invariant reciprocal effects and also time invariant cross-lagged effects, which is not necessary, but they do that here. But the article does not really make clear that the model that they present is equivalent to a regular RI-CLPM. You know, with 3 time points, there are 2 reciprocal parameters in the reciprocal model, and there are 2 residual covariances in the RI-CLPM. So you have the same number of parameters. So you have this model equivalence again, so that the reciprocal interaction shown in figure 2 on the previous slide is just one possible interpretation of the data. So I was interested in this data set, and I tried to get the raw data, but turns out that's no longer available 20 years later. But in table 2 of the article, you get the estimated covariance matrix for the saturated model, H1 model, where you take missing data into account. So this is by maximum likelihood, or what's called FIML. In this case, 76% actually have complete data for all 3 time points, so the missing data situation is not that bad. So what I did was to use this estimated covariance matrix for the saturated model as a sample covariance matrix, because that would give you estimates, point estimates of the parameters that are close to what the raw data would give. A chi-square fit and standard errors would not be correct. For that, you would need to go back to the raw data. On slide 37 then, we have the different models listed, the 3 kinds, the RI-CLPM regular kind, the reciprocal only kind, and the reciprocal models variations in three different variations. And I should mention, by the way, that throughout all of these 5 examples, I use the RI-CLPM, not the classic CLPM, because the CLPM fit is much worse in all of these examples, and the random intercept variances are substantively large and significant. in all of the examples. And in my opinion, the RI version of CLPM is the more statistically motivated, well-motivated model, because you have multi-level data, time points within people, and therefore you should have a multi-level model in essence, where you should have at least a random intercept, as we do in multi-level regression. So that motivates the random intercept component. Now in this case, CLPM compared to RI CLPM has only 17 parameters. You get rid of the 2 random intercept variances and the random intercept covariance, but the log likelihood then will be 9,200, and the BIC value will be 18,513. So much worse values than any of these models listed on the slide here. So here you have 2 RL CLPM, where the invariant cross-lagged effects, the lag 1 effects, reduces the number of parameters by 2, and you get the same log likelihood and therefore a better BIC. So clearly holding the cross-lags invariant across time is the way to go across those 2 time points. Now model 3 and 4 then are reciprocal only models. So the first one is equivalent to the first RI CLPM, and the second one you impose invariant reciprocals, which you don't need to do for the reciprocal only model, and thereby you reduce number of parameters to 18, and you get a slightly worse fit here in this model by doing so, but not by much. So you see then that imposing invariance of reciprocal effects does not fit as well in this case as imposing invariance of cross-lagged effects. We'll see in other examples that it's the other way around quite often. So then in model 5 you have the standard reciprocal model with the invariance reciprocals, the 2 reciprocal effects, the sets of 2 reciprocals are equal across time, and that model is equivalent to model 3 and to model 1, as we see also in the log likelihood. But then for the reciprocal model you can add invariance of cross-lagged effects to that and reduce by 2 parameters, just like you reduce by 2 parameters between models 1 and 2 up here. And you don't worsen fit at all there either, indicating once more with a different model that invariance of cross-lagged effects is reasonable. And then thereby you reduce the BIC value. And then you find in that analysis that only one of the 2 reciprocal effects, lag 0 effects, is significant. And if you put the other one at 0 and estimate the 1, then you reduce by 1 parameter, but the fit is unaffected, so that parameter clearly wasn't needed, and you get the best BIC here. Now I should just mention then that for model 7 the estimates are then very close to those presented in figure 2 that we looked at before of the Ormel article. So these values are probably fairly representative of what would happen in a real data analysis if we had the raw data. Note that I have not given chi-square fit or RMSEA at all here, because those would not be correct. Now, interesting little side note here for models 3 and 4, they had a hard time converging, and they would only converge if you use starting values that you can derive from RI CLPM using formulas in the Sparrow-Mutén paper. You can actually compute what they should be and then put them in as starting values. If you have an extra hard time, you can put them in as fixed values, and then once you have the other parameter estimates you can free them. But anyway, so that thereby I got convergence, but I got negative R² values, a couple of negative R² values. And when I tried to impose either one of the two restrictions, A or B, it wouldn't converge again. So in this case, and that's the only one of the 5 examples, the reciprocal only model fails, essentially. So on slide 38 then, you have the summary of 3 models, the best one of each kind. So the regular model here, where you have significance of both cross-lags, you have the effect of increasing disability at t-1 causes an increase in depression at time t, and vice versa. So you get both of those cross-lagged effects, whereas you don't have reciprocal parameters in the model. For the reciprocal only model, we have no solution. For the reciprocal model, we under the invariance of cross-lags and reciprocals, you keep one of the 2 cross-lagged effects, the dep to dis, but the other one, dis to dep, becomes a lag 0 effect instead. So the interesting thing is here that this model, model 7, is what the Ormel et al. Article presented and discussed and interpreted this difference in timing here between the effects. However, you have a model which is just as good up here, and it would say that there are no lag 0 effects, there are only the cross-lagged lag 1 effects, and they go in both directions. So that's an example of different interpretations of the same data using essentially the same models, equivalent models, I should say, not the same models, but equivalent, because they fit the data the same way. Okay, so then slide 39 goes to a third example, and this is the so-called BLS data, going back to depression and self-esteem as in the first example. Again, taken from the Orth et al. Article. So here we have 404 people, 4 time points now, and this is a time interval between the measurements of 1 year. So now you notice that we put back in the chi-square and p-values, etc., because here we have the raw data, and that's provided on the website for this Webtalk as well. And you notice since we only have t equals 4, we have much higher p-values here than ever before, because the model has only 9 degrees of freedom. Actually, for t equals 3, you would have only 1 degree of freedom. So it's not a very strong model in the sense that it doesn't impose that many restrictions as you have for t equals 5. And the t equals 3 model is an even less strong model from that point of view. So here we have RLC/PM and the invariance cross-lags, and the log likelihood difference is 2 for 4 parameters. 2 times 2 is 4, with 4, even though we should use a adjusted chi-square difference test because of MLR. We have the scaling correction factor. It looks like the invariance of cross-lags will win. Again, we have these high p-values and incredibly good RMSEA values. The reciprocals only model equivalent to the first one here, and reciprocals only with the invariant reciprocals has 31 parameters like the model 2, but they're not the same, and actually in this case invariance of reciprocals fits better. And then we go to the reciprocal model, which has the cross-lags in it, and we have the invariance of the reciprocals and the invariance of the cross-lags as well as the reciprocals down here. And we see that the log likelihood value does not increase that much, even though the number of parameters get decreased, and therefore we get the best BIC value in the whole column here, 3344. But you could claim that several of these models fit the data about the same, but they do have different interpretations. So on slide 40, we take a look at the interpretations. Again, the 3 key models, one of each kind, each type. And the interesting thing here is that for the BLS data, the regular RICLPM has no significant cross-lags. Nothing is significant there. Same thing holds for model 4. None. No lag 0 reciprocal. So no action at all here. But for model 6, you actually get a lag 0 effect that's significant from depression to self-esteem. And that's significant also with Bootstrap's confidence intervals. So that's interesting. You would find nothing by regular methods, but you find something of interest with the reciprocal model. And this model 6 may be preferred over models 2 and 4 because it does find a relationship between the two variables, and it does not fit worse than the alternative models. In fact, actually, it has the best BIC. We'll leave the last comment for your own study. Then turn to slide 41 for example number 4. And this is the NLSY 79 depression and self-esteem data that was also used in the Orth article. So here we're talking about a huge sample, 8,000 people, much larger than any of the others, and 11 time points, many more than the other examples. So again, depression and self-esteem, and here now measured 2 years apart. So this is the largest time interval for the measurements of all of these examples. And this example has quite low coverage and time invariant modeling using ML. The MLR H1 model cannot be estimated, so no MLR chi-square, and that's because of the low coverage. It may be a multiple cohort analysis that was needed for these data. Slide 42 then. You have the same set of models, and here now we see that the degrees of freedom increases quite a lot because of the 11 time points. So we have the invariance here, and at least the RMSEA seems to be reasonable in this case. Chi-square is high. These variables are skewed, so regular ML chi-square is not the greatest here. Reciprocal only model with invariance reciprocals over all of the 11 time points has a little bit better fit than the RICLPM. Model 3 reciprocal with the invariant cross-lags and reciprocals. It reduces the number of parameters quite a lot. And we see then that we can go further in that analysis and go down to model 4, where you have also a reciprocal effect only in one direction based on the analysis in model 3. So in model 3 versus model 1, we have how do they differ? We have 10 residual covariances here, across time, versus here we have two, both of them have invariance cross lags. Here we have two reciprocal effects, so 10 minus 2 is 8, and that's the difference in number of parameters here. It's good to keep track of that so you know that you set up your models correctly. It's easy to go wrong if you don't count the number of parameters. And here we see again that if you compare model 1 and model 2, invariance of cross-lagged effects compared to invariance of reciprocals have different implications, same number of parameters, but in this case invariance of the reciprocals across time fits the data better than invariance of the cross-lagged effects. So here, for the NLSY data, the conventional model has cross-lagged effects in both directions. They're negative. As self-esteem goes up, depression goes down, and vice versa. The reciprocal-only model, however, moves those effects over to lag 0, contemporaneous effects, reciprocal effects, of the same sign, but nevertheless not with a lag 1. And model 4 then keeps one of the cross-lagged effects and moves the other one over to a lag 0 effect. So one could claim here that model 2 contradicts model 1 and is partly supported by model 4. So that's interesting. Okay, the fifth and last example, academic self-concept and achievement measured by GPA, grade point average, and we'll call it the GPA data for short from now on. It has to do with French high school students, fairly large sample and a nice number of time points. And it's measured 5 times over 6 trimesters during first and second years of high school. No data for the 5th trimester, so non-equidistance here at one point of the time points. So what is that? That's what is it, 3 or 4 months apart, these measures, apart from between the last two. So it comes from an article that's analyzed in a new paper by David Kenny and Betsy McCoach. And here we're looking at, going to take a look at the reciprocal RICLPM with non-invariant cross lags and invariant reciprocals, model 4. So here we have on slide 45 for this model 4, we're looking at the effect of, this is the lag 0 effect of GPA influencing your academic self-concept. And you have then the Bootstrap distribution for that parameter, and you see that the mass of values are, concentration is around positive values 0.3 to 0.7 here. So, but you have the 95% confidence interval spanning 0, going from minus to plus, so we include 0. So you would call it non-significant. But it is to a large extent evidence of a positive effect. We'll see how it goes. If you look at the lag 0 effect in the other direction on slide 46, then the values center around 0, peak around 0, and we can conclude that that parameter can be fixed at 0. It's also insignificant here. On slide 47, we see a summary of the models we have fit to the GPA dataset. And to remind you again, we have 5 time points in this case. The first model is the random intercept cross-lagged model, where we have non-invariance among the cross-lagged effects because of the difference in the time interval between the last two measurements, last 2 time points. And we see that we have not too great of a fit. Even the RMSEA gets a fairly low probability of being less than the 0.05 value. Now we have the same time intervals between the first 3 time points, so we could have invariance for those time points. So crosslags between time point 1 and 2 equals crosslags between 2 and 3 equals crosslags between time point 3 and 4. So we get 2 crosslags for that interval, and then 2 more for the interval that ends at the end of the time points. And that model then has, instead of having 8 cross-lagged effects, 4 times 2 cross-lagged effects per interval, we will have 4 only. 2 for the first set and 2 for that last time interval between 4 and 5. So 8 versus 4 is a difference of 4, and that's a difference in number of parameters here. And that model fits a little bit better, a little bit higher probability of being less than 0.05 for the RMSEA. And if we look at the log likelihood, you have only a 2-point difference here. We multiply that by 2 to get a feeling for chi-square, and we have as many as 4 parameters difference between the models. So it looks like you don't get a worsening of fit going to model 2, although we have not taken into account non-normality scaling correction factors in the chi-square difference testing. So that's in the family of the random intercept cross-lag models, the model type A as we referred to it earlier. If we then turn to model type B, which is the reciprocal case, reciprocal only, we have nothing to report here. And if you look at the bottom, my comments here are for model 3, if we try a solution for the 44 parameter equivalent model version, or even the invariant reciprocals version, time invariance of reciprocals, we find that we cannot get a solution. No convergence or negative R-square values. And we can conclude then that model 3 is not suitable for this data set. And that can happen in some applications, in some data sets. If you then turn to model type C, the reciprocal model, which allows reciprocal interactions and cross-lagged effects, then we notice here that I go for a 42 parameter model, not the equivalent 44 parameter model, and that is again because of no solution, that I was not able to get a solution for the 44 parameter equivalent version which would apply only t minus 1, that is 5 minus 1, 4 restrictions on the 8 reciprocals. That is, for instance, 2 equals 3, 4 equals 5, time points 2, reciprocal effects for time points 2 equals those for time point 3, and reciprocals for 4 equal to those for time point 5. So 2 reciprocals per interval here, so 4 parameters. So 8 minus 4 is the 4 restrictions that we have, which would give us 44 here in this case. But again, I did not find a solution there, and instead I went to the model with full time invariance for the reciprocals. So that has 2 parameters less. Instead of 4 parameters, I have only 2 reciprocal parameters. So that model actually has a reasonable RMSEA as well. The BIC is not as low as for model 2. However, you can have a version of model 4 where you have partly invariant crosslags, just like you do for model 2. Partly invariant crosslags here reduces the number of parameters by 4 again, just like up here, to 38. And that log likelihood value that I'm not reporting here is 12,878. So once again, that partial cross-lagged invariance fits rather well, and then the big value would be 26016. 26016. So that would be the lowest and best big value of them all. But I'm staying with model 4 here just for simplicity for now. I essentially couldn't fit the other model on the page. And find then, in line with the Bootstrap distributions that we looked at earlier, that it's only a lag 0 contemporaneous effect in one direction. You can fix the other one at 0. And then you end up with this model with 41 parameters and the same log likelihood in this case, and a good BIC. Again, we could have imposed partial invariance for the cross-lagged effect. Turning to slide 48, we have a summary of the estimated effects for these three key models for the GPA data with t equals 5. So the first model is the classic random intercept cross-lag panel model, and we found significant cross-lag there from GPA at t-1 to academic self-concept at time t. That model does not allow any reciprocals. For model type B, the reciprocal only model, we could not find a solution, so we put that aside. For model type C, the reciprocal model, we had two different versions with non-invariant X-lags or with partial invariant X-lags. The results are the same with respect to what I'm reporting here. And we had full time invariance of the reciprocals with only a single lag 0 effect because the other one was 0. In that model, we find no significant cross-lagged effects and only a significant contemporaneous lag 0 effect from GPA to academic self-concept. So you see there that Model 2 and Model 5 disagree. And it's an example of the fact that using cross-lag panel modeling, you cannot really rely on findings of cross-lagged effects when you have almost equivalent or almost the same fitting reciprocal models that says that instead the effect is contemporaneous lag 0.